Have you ever wondered why an image becomes blurry? Or how a filter can remove noise from a signal? Or even why the word convolution appears so often in artificial intelligence? It may sound surprising, but behind all of these lies a powerful mathematical idea, one that plays a fundamental role in electrical engineering, signal processing, optics, and image analysis. In simple terms, when you perform convolution between two signals or functions, you slide one over the other and measure how much they overlap at each point. This simple idea gives us a way to combine two sources of information and understand how they influence each other. That's why the convolution has critical applications across many fields. In signal processing and systems, convolution is the main tool for computing the output of a system. If you know the input and the system's impulse response, convolution tells you exactly what the output will be. In image processing and computer vision, convolution acts like a filter. A small window, called a kernel, moves across the image and extracts features like edges, textures, or blur. In artificial intelligence and convolutional neural networks, convolution is the foundation of face and object recognition. Filters learn automatically to detect important patterns. Even in probability theory, convolution describes the distribution of the sum of independent random variables. In the previous video, we explored the fast Fourier transform or FFT and saw how it dramatically speeds up computations. But that naturally raises an important question. What exactly are we trying to compute so efficiently? One of the most important answers is convolution. In this video, we will understand how convolution is defined mathematically, how to compute it numerically, and why its connection with FFT creates one of the most powerful tools in engineering. This is not just a formula. This is the mathematics of response and transformation in the real world. So what does convolution really mean? To understand it, imagine we have a system. This system could be an electronic circuit, a mechanical structure, a digital filter, or even an optical setup. Now suppose we apply an input signal to this system. The output usually does not depend only on the input at the exact moment. It often depends on past inputs as well. In other words, the system has memory. For example, if you send a very short pulse into a system, its response may continue for some time. If the input is more complex, we can think of it as a combination of many small pulses, and the total output is the sum of all their responses. And that is exactly what convolution computes. A key idea in engineering is this. The output of a system depends not only on the present input, but also on its past behavior. Here is a very practical way to think about convolution. If you know two things, the input signal and the system's response to a very short impulse, then convolution gives you the complete output. So in practice, convolution answers this question. If I know the input and I know the system, what will be the output be? That's why convolution is so important. It is the mathematics of system response. Now, as you can see on the screen, this is the mathematical definition of convolution. For continuous time signals, convolution is defined by this integral. And for discrete time signals, which are very important in digital systems, we use this summation. At first glance, these formulas may look abstract, but they become simple when we interpret them step by step. Let's break it down using 4 intuitive steps. First, flip. Reverse the system response. 2. Shift. Move it across the input. 3. Multiply. Multiply overlapping values. 4. Sum. Add them together. Repeat this process for every position and you get the full output signal. This flip, shift, multiply, and sum interpretation is one of the most useful ways to understand convolution. Let's make this idea concrete with a simple example. Suppose the input is x equal to 1, 2, 3, and the system is 1, 1. Before computing, we can determine the output length. N minus 1 plus m minus 1 plus 1 equal to n plus m minus 1. This comes from the idea of overlap. Before the first contact, there is no overlap, so no output. After the last contact, again, no overlap, so no output. Only when there is overlap do we get valid outputs. Now step by step. First overlap, 1 times 1 equal 1. Next, 1 times 1 plus 2 times 1 equals 3. Next, 2 times 1 plus 3 times 1 equals 5. And lastly, 3 times 1 equals 3. So the final result is 1, 3, 5, 3. This simple example clearly shows how each output value comes from local overlaps. One of the most important applications of convolution is filtering. Suppose you're measuring temperature or reading sensor data, but your signal contains noise. How do we remove that noise? With convolution. Let's look at the simplest filter, the moving average filter. This filter averages neighboring values. Why does this remove noise? Because noise usually consists of rapid random fluctuations. When you average multiple points, positive and negative variations cancel out, leaving a smoother signal. Example: input 10, 12, 11, 25, and 10. The value 25 is noise. After filtering, 10 plus 12 plus 11 over 3 is 11. 12 plus 11 plus 25 over 3 is 16. 11 plus 25 plus 10 over 3 is 15.3. The sharp spike is reduced and the signal becomes smoother. All filters, from simple to complex, are built on convolution. Now, let's move to images. An image is simply a 2D matrix of pixel values. Convolution works the same way, but now in 2 dimensions. We take a small matrix called the kernel and slide it over the image. For example, using an edge detection filter, we first multiply corresponding elements, and then we sum the results. This highlights edges and sharp changes in brightness. If we change the kernel, first we do small positive values, which will blur, and then we do strong center differences, which will sharpen. This is exactly what happens inside tools like Photoshop and also inside AI systems. Convolution is the eye of the digital world. Now, we reach the most important part. The formal convolution theorem is shown here on the slide. This means convolution in time becomes simple multiplication in frequency. As shown on the slide, we can compute this using FFT in a much more efficient way. Let's compare complexity. The direct computation, O(n) squared, and then with FFT, O(n) log n. For example, for n equals 10,000, the direct method gives 100 million operations, and FFT gives 130,000 operations. That's about 700 times faster. This is why FFT is so powerful. It transforms a computational nightmare into a simple multiplication. In traditional engineering, we design filters. But in artificial intelligence, something amazing happens. The system learns the filters automatically. In convolutional neural networks or CNNs, early layers detect edges, middle layers detect shapes, and final layers detect complex objects like faces. Instead of telling the system what filter to use, we let it learn from the data. Without convolution, modern computer vision would not exist. Let's summarize everything in one sentence. Convolution is the language that systems use to respond to the world, and FFT is the fastest way to compute that language. We saw that convolution describes system responses, removes noise from signals, enables computers to see images, and becomes incredibly fast using FFT. I hope this journey into engineering mathematics was helpful for you. In future videos, we will explore even more exciting concepts. If this video helped you understand convolution, please like it and share it with your friends. Your feedback helps us create better content. Thank you for watching.